I'm going to show you how to speak computer. These handheld devices that we have, these smartphones, these computers, are so powerful because of one main invention: transistors. Well, what's a transistor? It's actually just a switch. It's either off, or 0, or on, 1. So how does a simple idea like just off or on translate into all the cat pictures and streaming videos that we love so much across the internet? Well, let's play around with this language and see what we can do. Imagine that we had 8 distinct lockers, each with a switch inside of it. If we wanted to start actually counting with these switches, we could just flip the first one up for 1, but then where do we go? Well, this is what is considered binary, the idea that you only have 2 states, and it's the language of computers. We can actually just keep carrying things over the same way we would with decimal in order to actually add larger and larger numbers. So we could go from 1 to 2 by moving over and flipping the switch on that side, and then flipping the switch back on the 8th block to 3, and then 4, and so on. This gives us a total of 256 different states that we can describe using just on and off. Well, what if we wanted to represent something like a negative number? Well, we could just take that first locker and use it as a switch to denote positive or negative. And in fact, this is how computer memory actually works. It's really just mapping these different states to mean different things. So let's take that and let's go in one level deeper. Rather than having 8 bits, let's actually represent just one locker as 8 bits, or a single byte, and move that kind of out so that we can represent, a single number more concisely. Okay, so if we have 4, and let's say we had like a bunch of other kind of random numbers, what else could we express besides just numbers with this kind of counting system? Well, we could actually map those numbers to mean different symbols. For instance, we could actually have them be letters and say that A equals 1, B equals 2, etc. It's not exactly quite like that. You actually start up in the 60s when you're doing character calculations, but you can get the point that you can actually store character data as numbers if you had a system that you could rely on. The idea of storing little bits of data in these lockers is a really good metaphor for how allocation actually works inside of the Java virtual machine. Accessing memory is just as laborious as having to go from one locker to another to open and access data. That's the reason why computers like it when you store things contiguously. If we want to have a bunch of things that are very similar, we can actually put them in memory all next to each other. Computers are very good at accessing memory that's stored contiguously in a row, kind of like a bully who's running down the hall and opening all the lockers up at once. The problem with running down a hallway full of lockers like this, though, is you need some indication of where to stop. We use something called a null terminator to describe where you actually want to stop data. This is just a symbol to represent a kind of special code, which means, hey, stop reading the other lockers. So it allows you to put something actually in memory and then have the computer run to it and stop. Now you can imagine that if you had millions of lockers, you could store some pretty complex data. Well, the one problem with that is, as you saw, we can read and that's fine, but with larger and larger data sets, we're going to have to read a lot more data and move to a lot more lockers if we ever wanted to actually move data around. Now comes one of the coolest things that you can do with memory. In order to actually describe that dog is in locker 1, 2, 3, and stopping on 4, all I really need to do is describe locker 1. If you knew that I'm going to have to go to locker 1 and run through it until I stopped, then you could just store that entire dog word in locker 5 using a pointer. In fact, you could store the same data in locker 6, 7, and 8 and use up only the same amount of memory that it took to originally store it. This idea of referencing data is a fundamental aspect of Java, and it's incredibly efficient at being able to point to data without having to copy it. You can see that in memory, the type of data is really important to be able to know how to actually get it out of these lockers or out of memory. So I'm going to show you now all the different types that you need to know in order to be an excellent programmer. There's basically 2 kinds for Java. There's primitive data types and reference types. Primitive data types start out with just the simple Boolean. Think of that as like a switch. It's either 1 or it's 0, on or off. One that requires a little more storage is the byte. This is basically 8 different switches. We'll often use it for storing just raw information. Next we have our numbers. Basically all of these are integers. So short integer, an integer, or a longer integer, each one having a little bit more space for a bigger and bigger number. They're also all signed, which means that we can express them as negative or positive numbers with that type of data type. So numbers are all well and good, but we are going to also need characters. It's going to make it much easier for us to express ideas like words. And finally, there's floating point data types. If you ever wanted to express something like, 3.14 or anything with a decimal point, if you wanted a little bit of precision, you could use a float, or with more precision, you could use a double to express that floating point, almost like a scientific notation. And now for the other side of the column, reference types. Under reference types, there really is only a reference type. It's just a memory address. It's just storing a pointer to some other place in memory. And this is what's going to allow us to build incredibly complex pieces of data by combining the primitive data types with the reference type. So as you can see, each of these kind of increases how much you're using of that memory a little bit and a little bit. As programmers, we want to use the least amount of memory needed in order to be efficient. By doing so, you'll have a lot more space left over for building your awesome applications.